Okay, there we go. Hi, everyone, and warm welcome to today's webinar. My name is Cecilia. I work at the Division for Internationalization with International Student Recruitment, and I'm joined here today by Professor Valentin Troll, who is going to talk today about his research about volcanoes and about, his work at Uppsala University. We will end today's webinar with a Q&A session. So if you have questions about the presentation or about the content of today's presentation, feel free to post in the Q&A box. We won't be able to answer practical questions about the application, such as, supporting documents, scholarship application, etc. So if you have those kinds of questions, please send them to us via email instead, because today is all about volcanoes and about Professor Troll. So with that being said, I will hand the floor over.
Thank you very much, Cecilia, and it's a great pleasure being here today. And I see that people from all over the world are joining. This is exciting. So thank you for joining in this morning. And yes, I'll talk a little bit about my research. I'm a specialist when it comes to volcanoes. I work with volcanoes in all aspects, and I'd like to share some views on that. I also want to kind of stress that volcanoes are not just bad, so I will share my screen now. And Cecilia, can you let me know whether the screen works?
Yes, we can see your PowerPoint
Wonderful.
window.
And this is now the full PowerPoint projection mode, so you can see my screen. And yeah, I'd like to stress today that volcanoes have two faces. This is my important message, and I'll come back to this several times during my presentation. There is, of course, scary aspects, but there's a lot of beneficial aspects. And this is, of course, the case with many things. And this is what I'd like to bring across today. So volcanoes as a source of hazards and as a source of resources. That's the things we hopefully going to discuss today. So first of all, I'm going to give some fundamental points about volcanology and volcanoes. Then I will talk a little bit about myself, and then about my activities. And then I'm going to spend some time on volcanoes as a resource, because I think this is the underappreciated side. And then I will also touch very briefly on volcanoes and culture towards the end of my presentation. So, well, I think we need to realize that magma is one of the most important probes into the Earth's interior. When we want to learn about the Earth's interior, we can only drill a few kilometers. The deepest drill hole is 12 kilometers, and anything beyond that is very hard for us to actually get a hold of, to access. So what we do is we look at magma as a probe, and this tells us something about the source region of the magma that's being brought up from volcanoes, but also about the rocks that have been passed by the magma during its journey to the surface. And because magma, and once it's erupted, we call it lava, is very diverse, you need a bit of knowledge. You need to understand the language of magma, and that's what petrologists do. Petrologist is the science of rocks. So my training is in rocks, and I read rocks, so to speak. So here's the kind of concept. If we have an eruption at the surface, we know it's connected to a much, much larger system at depth. And this is what we don't understand fully. And here we can make inferences from the rocks that have erupted about how volcanoes work inside, how the Earth works inside. And what I do to that effect is use quite a wide variety of approaches, and to assess the sources as well as all the processes magma experiences when it moves to the surface. This, of course, includes field work, but also experimental and numerical simulations of processes, but also petrological, geochemical, and isotope studies. Isotopes are elements that have different atomic numbers, have varieties. And here we can actually look at variations. This is a bit like rock DNA, if you will. And targets can range from hundreds of kilometer scale to individual volcanoes to very small kind of analysis of individual crystals. And this depends on the question we are asking and on the answers we are seeking. So I think I should stress that the volcanoes we see at the surface, they're only very small little cones compared to what we call the volcano-magma system. There's a big connection to the Earth interior. And to understand the full volcano-magma system, we must realize volcanoes are like the tip of the iceberg. There is a lot more, and we have to use a lot of different methodologies, and there's a lot of different aspects that come together to understand the system as a whole. So people will look at the hazards at the surface, and you can measure the chemistry of gases, for example, and that of course has influence on the atmosphere. There's volatiles that are added from volcanoes, and then if we want to look deeper, we often use geophysics, or we can assess the ores that form inside volcanoes. We can also look at how volcanoes interact with tectonic processes, with plate tectonics. We can make experiments to understand these volcanoes. We can look at the minerals and crystals in there. We can determine the depth at which they have grown. We can do geochemical studies. And we can also look at processes in the deep mantle, what happens at depth. And these methods allow us to come up with a much more comprehensive picture. So what are we using all this for? Well, importantly, we need to assess hazards. And this is to avoid disasters. And volcanoes, of course, can cause disasters. And this is a very important aspect. But volcanoes will also produce energy, geothermal energy, for example, and a lot of natural resources. And I'll talk more about this later. And of course, we also want to understand fundamental geological, volcanological, and geochemical phenomena that occur on our planet. So my mission is therefore to understand the dynamic interplay of magma generation, magma processes, the transport of magma, and the eruptive behavior, and all the information we can glean from that for the processes that are relevant to society. What are the processes relevant to the society? Well, the hazards, the energy that we can potentially harvest from volcanoes, and the resources. So here a few words on hazards. So here is an image of Vesuvius volcano in Italy, and this sits right above Naples. And this is an old drawing. Naples is a lot bigger these days, and this is one of the problem zones in Europe where a lot of people live close to a very active volcano. And the last eruption of Vesuvius was 1944, and it erupted many times between the big devastating Pompeii eruption of 79 AD. And here we really have to worry a little bit. So what can happen? Well, there can be big eruption columns and ash fall. And this is a big problem in many volcanic areas. But there's also more local hazards like lava flows and glowing avalanches, pyroclastic flows. There could be little domes of sticky lava. It's a bit like toothpaste coming out of a volcano, but once it cools down, they can break off and cause landslides. So these are all aspects that we need to consider when working with volcanoes, particularly in densely populated areas or in areas where infrastructure is very important. So this is the very direct effects and the immediate effects, but we also need to think about long-term effects. And here is a few ideas what the volcanoes can do. Immediately, hours and days during and after an eruption, we have the pyroclastic eruption, we have the lava flows, the ash coming down, but ashfall can continue for days, potentially weeks after the eruption. And also the gases in the atmosphere can cause some problems for the global temperatures. And it's known that global temperatures can change by ½ degree after a big eruption for several years. And therefore, climate effects may be a problem. And if you also think of areas with thick ashfall, removing all the ash may take quite some time. So the cleanup is often a problem for, in some areas, for actually months to years after the eruption. So, and I said it before, volcanoes usually have a bad reputation. And this is because when you look in the news, you will usually see images like this. So this is Hawaii in the top left, where lava flows are going over roads, for example, destroying infrastructure, or the images to the right here and the bottom left. That's from Italy, from Etna. There we see lava flows intruding into the world of humans. And here the digger is trying to dig a ditch in order to divert the lava flow. But if the lava is big and comes with enough volume, there's usually very little humans can do. You cannot stop a lava flow of this dimension. And I've just seen it recently on La Palma. People were trying to save a church by digging a ditch, but it was in vain. The church nevertheless fell 2 days later. And we have no ways of stopping that. So what we need to think about is how to deal with that. So, and for that, we monitor active volcanoes. We have different methods of monitoring, and this helps us to make predictions about when a volcano will erupt, how a volcano will erupt, and this will allow us to evacuate people, to protect infrastructure, to build infrastructure that is resilient, to create communities that are resilient. So here we can measure geophysically, but also we can measure the rocks. And this is what happens at volcanoes. Increasingly, we use also remote sensing, like satellite-based radar interferometry, like the image on the bottom right. It measures whether the volcano is bulging up or whether it's calming down. And if we have many of these measurements, we can usually work out if a volcano is in unrest or not. So if we have seismic activity increasing, if the volcano expands, if there's more gas coming, if the heat flow increases, then we can actually say, oh, this volcano is waking up. And by now, if a volcano is well monitored, we can actually be quite good in predicting when a volcano will erupt. So it's not about an hour, but we can say in a week or so, this volcano might be ready. And this gives you time to prepare. Very important. So now a few words about myself. I was born in southern Germany, and then I started to do my university education there. After 2 years, I moved to Scotland, to St Andrews, and I got my bachelor degree there. And then I moved back to Germany for my PhD at the GeoMar Research Center. And then after that, I was working as a lecturer and then later as associate professor in Dublin at Trinity College. And then I did my habilitation, or in Sweden, it's called the docent, in France. And then in 2008, I was appointed as the chair of petrology here at Uppsala, and I have been here ever since. So, and the university kind of did some little report on me a few years ago. They called me the volcano researcher who speaks with rocks. So indeed, I like to think this is what I do. I have a good sense for rocks, and I worked with rocks ever since my undergrad training. So rocks are complicated, and they can be read if you understand their language. So I interact a lot with rocks and what we can learn from rocks and how we can use rocks, and this is my specialty. So this is areas I'm involved in certain projects, and I've seen many parts of the world. Some parts I haven't yet seen, but I'm still keen to see the other parts that are open on this map. But I work, of course, in Scandinavia. I work in the North Atlantic, including Iceland. I work in northern Canada. There's some old volcanoes there. I've worked in Central America. I've worked in the Canary Islands and the Cape Verde Islands. I have some work in South Africa, but also big projects in Indonesia. And then I worked a little bit in New Zealand as well. So I will show you some examples of my work, but let's talk a little bit more about myself, first of all. So geological work usually means it starts with fieldwork. You have to go out, and this is the adventure part of it. So I had an intriguing interview the other day with a newspaper journalist about the La Palma eruption in the Canary Islands. And afterwards, after the interview, I saw he referred to me as the Indiana Jones of volcanology. I think all volcano researchers are a bit of Indiana Jones, but this is the adventure part. And it's, of course, very enjoyable if you like that kind of thing. So you go out, look at volcanoes, you take samples. Sometimes you have the opportunity to look at a volcano from above with a helicopter, but you also have to take your protective measurements very seriously. You will have to work with gas masks and things like that. It's not always pleasant. So, but then you get the opportunity to look at active volcanoes. Etna has been erupting earlier this year. It's still erupting at the moment. And here is some images from February this year of Etna erupting. The eruption zone is not populated, so it's not dangerous for the population at this point, but it's spectacular to watch. And I think one of the biggest disasters that happened in Europe volcanologically this year was the La Palma eruption. And I've just come back from La Palma 2 days ago. And here the volcano started to erupt in the hills above some settlements, and the lava is actually flowing down into these villages. And this is a bit of a problem. And here there's a lot of interest because a lot of people are affected. Almost 8,000 people are evacuated now. More than 2,000 houses are destroyed. More than 1,000 hectares of plantation land is affected. So this is quite serious. And what we do there is we're looking at how the lavas progress. There's a map in the top left about how the lava field has developed over time. It starts off small and then it grows, and then this helps us to say something about where the lava might go next. There is also some aspects about growing of land, and this will of course influence the biosphere, the marine biosphere. And of course, all of this will help us to say something about which areas are at risk, and it allows us to warn people. And there's an image of evacuation, of ongoing evacuations. Whenever there is a village that might be affected by lava soon, we have to ring the alarm bell and get people out. So once we have looked at the field and we've taken rocks and we studied rocks in the field and mapped them, we have to bring samples back to the laboratory. And we work here in Uppsala, but also at our national geochemical facilities in Stockholm. And the top right image is the iron probe in Stockholm, and the top left, the bottom left image is the electron microprobe here in Uppsala. And there we can look at rocks. The big rock up there is actually from the Iceland eruption that happened earlier this year. So we can then look at the crystals inside, and we can get information about how the volcano works in its belly inside. So, and once we have looked at rocks and once we've done the field work, a big important aspect of academic work is we need to publish these results. And I find this personally very enjoyable. I enjoy writing. I enjoy expressing myself and my ideas via writing. So it's books and articles, and here's just some examples. And every now and then you have these really touching moments like this photo in the middle here. I've just been to the visitor center on Tenerife, and they are selling my book. So I was really, really happy. So I was very pleased about that. So this is one of these moments where you think, wow, so I wanted to share that with you. So then when it comes to teaching, importantly, as an academic, you have three main tasks, and that is research, teaching, and outreach. So I'll talk a little bit about teaching. I teach some large classes, but I often try to break them down into small groups. I think small group teaching is extremely important, interacting with individuals and working with individuals in respect to their individual learning styles. None of us is the same, we're all different, and therefore small group teaching allows you to work more closely with people. So plenty of practical exercises and small group teaching is my personal philosophy, because we're all very diverse. And I've been an international student coordinator at my previous job at Trinity College in Dublin. And I have teaching experience from different European, but also non-European countries. And I realized that we need to interact on a close basis in order to really get the optimum learning experience for all the learners involved. So I use this Chinese proverb a lot, listen and forget, see and remember, but do and understand. So this is where my philosophy comes from. I try to be very hands-on, and this is, in my experience, very enjoyable for myself, but especially for the students. So this is where I come from when it comes to teaching, and that includes, of course, field teaching. So here's a few impressions. The top left image is some rocks in Sweden, but then there's also other field trips. We do international field trips to warmer places than Sweden, but Sweden is, of course, very fundamental because we have a lot of very good geology and a lot of deposits, ore deposits, for instance, that are economically very important. Many of them come from volcanoes. And this is very good for educational purposes as well as for future job prospects. A lot of geologists that graduate here actually find jobs in the mining industry. And I should stress that the Swedish mining industry has a huge demand that cannot be filled by just graduates from Sweden. So if you are interested in a job like that, that might be an avenue for you. So there is probably 3 to 4 times more people demanded by the active mining industry than we can produce. So, but part of academic life is also examinations, and if examinations go well, there will be celebrations. So here's a few impressions, and sometimes you have to kind of go to an exam. It's often very formal exams, are strict matters. And then you usually have a little party, and there's an image of a little garden party after last year's, no, 2 years ago, prior to Corona, with some of my master students, and then some images of exams I was involved in, like in Iceland for PhDs or in Germany for PhDs, with students from all over the world. So, and I'm very proud of this. I work a lot with students, and for my PhD and my undergrad, masters, and bachelor students, we were rewarded a lot of prizes over the last 20 years, and I'm listing them here. I'm not going to go into details here, but I like to think that interaction with students pays off if you work closely with them and they engage fully in this experience. Then it usually produces very good results, and I'm very proud to have a long list of prizes that my students have received. So I said my third task besides research and teaching is outreach. So I'm pretty active in outreach as well. And so I have been involved in advertisement campaigns that involves volcanoes. I have been reporting for projects and for larger national projects like the CNDS project here, but I've also been on television a few times, like Daily Planet and things like that, whenever there's something big happening, but also for Swedish television, of course. And just recently we were on La Palma, I mentioned it, and there was 2 film crews with us, one from the BBC and one from National Geographic. And so we are recording some of the work and making it accessible to a wider audience. And if you do things well, then every now and then you get the honor of getting a little award if you do a good project, or if you do some good teaching. So here's some recognitions, some impressions of recognitions. And I'm showing them not so much about myself, I'm showing them to show you that working in academia can be very rewarding. So, here now, I'd like to go to the second part of my presentation, and this is the important message I want to bring across to you, and that is volcanoes, as I said, often have a bad reputation, but I think we have to take a step back to be more reflective of this. Volcanoes and their underlying magmatic processes are the principal agents of redistribution of materials within our planet. They therefore are a key feature in understanding any localized concentrations of metals, of minerals, of fluids. And therefore they are crucial for humans and for our life on the surface of the planet. So this is what I'd like to stress for the next few minutes. When it comes to volcanoes, we often forget that we are touching volcanic products every day of our lives. Metals and ores are dominantly volcanic in origin. Many gemstones are actually volcanic in origin. We still use a lot of sulfur that comes from volcanoes, and there will be more sulfur from volcanoes, because once we go off fossil fuels, we will have a problem with sulfur, because most of the sulfur we're currently using is a byproduct of fossil fuel refining. And once we're off fossil fuels, we will have to produce sulfur again, and the best source is volcanoes. Building materials. Volcanoes make wonderful building materials. They make good stones and rocks, and we often use it in industrial applications, like for abrasion and for geothermal power, of course. And actually, there's quite a lot of food, drink, and cosmetics that connects to volcanoes, and I'm going to run you through some examples that I find rather enjoyable. So first of all, I mentioned before that many of the metals that we are needing for industry, also for green technology, they come from volcanoes. And here's a few of my students visiting a big mine here in northern Sweden. And Sweden is the biggest producer of iron, in the EU, and this will go on for many years. So there is a lot of job opportunities for well-educated geologists, and they require an understanding of principal volcanology because the rocks here are old, but they formed in volcanic settings. So volcanoes have a practical use here in Sweden, despite the fact that there is no active volcanoes here. So, and when we think of iron, copper, lead, silver, and many of the rare earth elements, these kind of rare metals that are very critical for many industries these days, then most of them come from volcanoes, particularly copper. The most copper at the moment comes from the Andes in South America, where we have these large copper deposits. But, well, and that's a volcanic region. Most silver comes from there as well. And many of the gold deposits can be also volcanic, not exclusively, but many are. And iron is the most important metal. If you think of building a bridge, you need a lot of iron, and iron is, for most parts, volcanic in its fundamental origin. When it comes to critical metals for green technologies, solar panels, wind turbines, but also for IT applications like mobile phones, and importantly for electrifying the traffic, batteries, we need a lot of these rather rare metals that we only need to larger quantities over the last few decades. That's the rare earth elements, the lanthanides and actinides of the periodic table, but also cobalt, manganese, and lithium. These are battery metals, if you will, and they come from volcanoes. The rock sample I'm showing here is actually a submarine rock. We got this from the Canary Islands. The lower part is a tuff, and the upper part is a manganese crust. This is material that comes from the volcanoes and settles out as fine dust and precipitates on the ocean floor. This material has a lot of manganese and a lot of cobalt, and this might be something we need to take into account in order to actually electrify the traffic, because we have real shortages of these metals at the moment. So, and when we think of lithium, another important battery element, we have also too little of that right now. And here's an image from the Andes, from the high Andes in Chile. This was a trip in 2018, and there you see one of these salt lakes, and the white is not actually snow. The white on the volcanoes is snow, but the white on the salt lake is actually salt, and that has a lot of lithium. And this is what we might need to quarry in order to provide our industries with enough lithium for electrifying the traffic. And there is some work going on, of course, and people are exploring this. So there is a lot of these salars being increasingly exploited. There's a lot of environmental issues there as well, because some of these processes reduce the groundwater, which is very bad for the local population. So there is industrial as well as sustainable aspects that need to be worked on and considered. Big challenges for the future. But here's some impressions. It's a growing industry, and there is a lot of potential labor possibilities for people in those areas. But as I said, there's also a lot of challenges, and a lot of good work is required to balance these things against each other. So then I mentioned gemstones are often volcanic, and most big diamonds are volcanic, and they come from kimberlites. It's a special rock type, and they are very pronounced in South Africa, in Australia, and places like that. And most big diamonds are actually volcanic in nature. So something I should not forget is that most old tools, humans' first tools, were often volcanic stone, because obsidian or volcanic glass breaks very, very sharp. And this has been used as spear heads and arrow tips and things like that. And I should stress that obsidians are coming back into fashion as a cutting tool, because they are actually a lot sharper than steel blades, and a lot of surgeons these days increasingly prefer obsidian blades, and they make a cleaner cut, and then your wound from your surgery heals better. So this is quite fascinating. I find that some of these ancient traits are coming back in fashion because they have some advantages. So this is actually something that volcanoes have given to us humans. We must, I believe, not forget about that. I mentioned sulfur before. Well, sulfur is traditionally used for two purposes, for disinfection and for making gunpowder. And we need gunpowder in order to quarry, for example. Some people are using it for bad purposes, but we need gunpowder for making a tunnel. We need dynamite. So, and this is very important. I mentioned earlier, sulfur will have to come increasingly from volcanoes again. The image on the left is a sulfur quarry inside a volcanic crater in Indonesia. And the image on the right is an abandoned sulfur quarry at 5,000 meters altitude in Chile, which I visited 3 years ago. And this will potentially be reopened. And here I'm also showing some matches, some Swedish matches. They're called Vulcan matches. And this is because originally the sulfur was from volcanoes, but disinfection is also very important. And many disinfection agents, like this particular soap from China, which is good if you have skin problems, they use sulfur for these kind of purposes. So I should also point out that white gold, porcelain, is actually largely volcanic in origin because the minerals, they come from granitic rocks. There's feldspar, quartz, and often clay minerals. That is a decay product of granites. So porcelain has been a huge game changer for humans on this planet because we can actually wash the plates. We don't have to have a wooden plate that starts to get smelly after using it 10 times and things like that. So for hygienic purposes, porcelain has been tremendously important. So this is volcanic in origin in its essence. Now, having mentioned this, abrasion and pumice rock, pumice stone is often used for this. Stone wash jeans came up when I was a teenager, and I always wondered what this meant, but actually I worked it out. It's pumice stone that causes the kind of stone wash jeans effect, and this is what it's done. It's tumbled in a big tumbler with stones, and then it gives you this worn out effect. But this abrasion aspect is not just applied to jeans, it's actually applied to foot scrubs and all sorts of beauty products that peel your skin. And here's a few examples there. So if you use any of those, you are actually touching pumice stone, like here, for example, you see the pumice stone in there, or pumice foot scrub, etc. Then you're actually touching volcano. And not just for your feet, actually, if you use this whitening toothpaste, there's often very finely ground up pumice stone in the toothpaste. It abrades the kind of, you know, things on the teeth you don't want. And so you actually might be putting volcanic rock into your mouth in very small quantities if you use this type of toothpaste. But I'd like to talk a little bit more about energy now. This is a big geothermal energy plant in Indonesia, and this is in Java, close to Sumatra. This is in West Java, and here we see that there's a big elaborate piping system that channels volcanic steam into an industrial application that allows you to generate energy. And this is relatively clean energy because the volcanic steam would be produced anyway. So whether we are having it poof into the air or whether we're actually using it makes little difference to nature, but a huge difference to us humans. So how does this work? Well, we have a heat source at the bottom somewhere, a volcanic heat source. And if we have water coming close to it, it will heat up. You can either pump the water there yourself or you take water that's coming anyway. And once this is hot, it can drive turbines and you can make electric power. The top right image is a power plant in New Zealand, in Wairaki. And one problem we have with these systems is that the pipes, they get clogged very quickly. And I'm showing an image in the bottom right of a clogged pipe. But you have to replace the pipes quite frequently, kind of once a year. But the material inside these pipes is actually very useful because first, it contains a lot of silver and people are taking it out to take the silver out. And if you mix it like they do it in Iceland, it's actually good for cosmetics because it's good for your skin. So here, the Blue Lagoon in Iceland is a geothermal pond that comes from the leftover waters of a power plant. It's a big tourist attraction, and they're selling these skincare products, and they're very popular. And this is some impressions from Iceland. This is the Blue Lagoon in the bottom right. And as I said, it's actually a byproduct from geothermal power production on the Reykjanes Peninsula, where the recent eruption happened. And this is the main power source for Reykjavik. And here's just a little bit of a feel for you. 40% of the geothermal power in Iceland is used for electricity, then 43% for space heating, and then they can heat swimming pools, they can have fish farming, then they can heat greenhouses as well. And in fact, surprisingly, Iceland produces a lot of bananas, believe it or not, because of the greenhouses. So this is what cheap energy does in Northern Europe, for example. So a few more words about volcanic rock as a building stone. It's a very fine building stone. Basalt is very solid, and tuff is a good insulator. So depending on the different types of volcanic stone, you can use them. And I'm showing here the cathedral in Clermont in France. And this is entirely built of volcanic rock. So volcanic rock has been used for many, many generations. And this is a little church in Tenerife on the Canary Islands, which are volcanic in origin. And you see the brownish rock, and I'm also in the quarry here in the top, in the bottom left. And in fact, this rock is very porous, and it's light but very sturdy. And most of the big cathedral in Central and South America actually built of this rock. And in the Canary Islands, the Spanish Empire was trying a lot of things, including the building of colonial churches. And here's one of the earliest ones at a village called Arico. So, but volcanic rock is, of course, used all over the world. So the biggest Buddhist temple in the world is in central Java. It's Borobudur, and that's built entirely of volcanic rock. And very close to it is a gigantic Hindu temple. They're all about 1,000 years old, or a little older. And that's Prambanan. And here's some images of the Buddhist as well as the Hindu temple. And they're all built of the volcanic rocks coming from this volcano here in the bottom right. And that's Merapi volcano, one of the most active volcanoes in the world. It's 3,000 meters tall, and it has inspired not just the industry in the area, but also the culture quite dramatically. Now, coming back to Europe for a second, in Italy, where we have a lot of volcanoes, the use of volcanic stone is going back to the Roman Empire, where people have developed the first cement, actually, the Pozzolana cement. It then got forgotten in the Middle Ages, and now we're rediscovering it. So this is also a volcanic phenomenon that has been exploited. And volcanic rock can be very sturdy. It's great for millstones. Most really good millstones are made of volcanic rock. And it's a fantastic cement supplement. Volcanic rock is often ground up and added to cement. And here I'm going to show you some images. This is volcanic tuff deposits in Indonesia. And this is at Merapi volcano. And it looks a bit random the way this is quarried, but not just are they extracting the material for cement, they're also creating a sediment trap. If there's a new eruption, actually, it will be slowed down because of this random kind of ripple effect in the ground. So here we have good things for humans, but we also kind of minimize the effect of the next eruption. So a few words about agriculture. Here we see that volcanoes can actually produce a lot of fertile soil, and this is an example from Indonesia again. So here, tropical spices grow very well on volcanic soil. Coffee is also very important. Most of the coffee is actually grown on volcanic soil. And the biggest coffee consumers in the world is actually Scandinavia. And so we in Scandinavia drink a lot of coffee because it's so dark here. And this comes usually from volcanic regions. If you go to these areas, you can see some of these coffee plantations that are built inside volcanic craters, like here in East Java. And you can actually do some studies on coffee and how the volcanic soil affects the coffee. So here's the development of coffee beans from this volcanic crater up to the final product. Tea is also often grown on volcanoes, so I don't want to go into much detail. So is chocolate, by the way. Here's some chocolate beans from Indonesia. So if you like chocolate, then you probably have touched volcano. And some brands are capitalizing on that. The most famous brand in Iceland is actually called Lava. So chocolate is often linked to volcanoes as well. So is wine. Here's some wine from central France, grown on volcanic soil from the Canaries, but also from Etna, for example. And this is very good for the wine. There's a lot of minerals in volcanic soil. And here's some impressions from Lanzarote in the Canary Islands, where they grow wine in very complicated, very dry conditions. But the volcanic soil is good because it stores a lot of water, allowing you to grow the wine even in very difficult conditions. Now, I'm closing here the last 2-3 slides. This is volcanoes and culture. And this is a very important study that, or aspect of study, and that is wherever there's volcanoes, there's also cultural influences. This is the Meru volcano on the left. I visited it a few years ago. It's the one that just caused the big eruption in East Java, killing some people, unfortunately, and causing a lot of devastation. But here on the right, we see what's called a fire dance. This is Javanese people trying to persuade the volcano to calm down. It's an interesting phenomenon. I think it helps people to cope with the situation a lot better, but I'm not sure it does actually change the volcanic eruptions very much, but it helps the society. So, and volcanoes in Japan have been inspiring art ever since we can remember. And in fact, if you think of mangas, Japanese drawings and cartoons, they started with these volcano drawings. And here you have actually one of the first mangas, one of the first comic strips, where you actually have riding bubbles and a volcanic event coming together. And here's some more elaborate ones from Hokusai. They are several hundred years old, but these are effectively images that come with a little bit of text. And of course, it goes further. In Europe, we have writers like Jules Verne, who have the idea of traveling into volcanoes and seeing the center of the earth. And it continues today. Hollywood is still exploiting volcanoes, and there are several movies that do that. And just for my daughters at home, they like Disney movies with, for example, volcano ghosts and spirits being involved. So I just want to kind of highlight that volcanoes are very important from a geoscience aspect for a sustainable future. And here I'm showing this diagram by the Geological Society of London, and I'm in red encircling the area where volcano research comes in. It's about hazard mitigation, it's about technology and mining and minerals, and it's also, of course, about science outreach. So I'd like to thank you, and maybe I've been a few minutes too long, but excuse my excitement for that. So I say thank you for your interest, and if you have any questions, I will do my very best to answer as many of them as I can.
Thank you very much for that very interesting presentation. We have quite a few questions, actually.